So, real quick, before we do finding the series for ln of x, because we're not ready to do that yet, okay? I want to go back real quick to yesterday we did, or whatever day, you guys know what I'm talking about. We had f of x equals 1 over x, and when we did that one, we had it centered at a different place than what was obvious. Does that make sense? Okay, so would you guys be comfortable with me saying, if I wanted to make this as easy as possible, I might make this, I need to have a 1 here, yeah? Minus. And essentially, if I add a 1, I got to subtract a 1. And I need my x to have the same sign, so it would kind of look like that. Is everybody good? I'm sorry? No. This for right now, just pretend. We're just going to do f of x. Everybody good? Okay. And so finding my power series from this so I can get it into that geometric form. Okay. So now I call it and say, well, that means f of x is equal to n equals 0 to infinity of 1 times 1 minus x to the n power. We still feeling okay with this? Okay. And, I might call this negative 1 to the n and then x minus 1 to the n, just to make my figuring out my center, right? And the convergence and all that kind of stuff a little bit easier. Is everybody comfortable with what I've got so far? And this converges when absolute value of x minus 1 is less than 1. Because geometrics converge when the radius is less than 1. Are we all feeling comfortable? This is building off of what we did on Monday. Okay, so my radius of convergence here is 0 to 2. Or my interval of convergence would be 0 to 2. Solving negative 1 is less than x minus 1 is less than 1. Okay? And so if I can do that 1 over x, now if I say, all right, I want to find the power series for ln of x, one of the things I could do is say, well, that 1 over x is equal to the sum of what we just said. So if I want to find the power series for f of x, I can just integrate both of these. And now I have ln of x is equal to, what is the integral of this going to be? Well, for each term, it's still going to be alternating. Then the integral of x minus 1 to the n would be x minus 1 to the n plus 1 over n plus 1. Now, does this converge? Or where does this converge? Well, the rules for integrals is that the interval for integrals is the same. Right? However, we have to recheck those endpoints because the endpoints might converge for one but not the other. Okay? So I'll check 0. I'm having a problem. I'm having a problem. Still having a problem. Does anybody want to guess what my problem is?
You just made a new alternating function for the first one.
Mm-hmm. Oh, got it. This will take care of it. Great. We're good. So, are you... Are we good in terms of what's going on? Because the alternating component's still there. Because I ignored this piece. So that's part of my, like when I plug it in for x. So like when x is equal to 0, this actually becomes -1 to the n plus 2 over n plus 1. Does everybody see that? And I said n plus 2. Oh, wait. Is everybody good? Why is that? And then knowing that, you guys, what do I about? So this is helpful. It's something to think through. In fact, it'll lay the groundwork for some of what's coming. You guys, what can we say about 2n plus 1?
It's always odd.
It's always odd. Is everybody with me? So, like, because 2 times 1 plus 1, like, it's going up by 2s and it's starting at an odd. Okay? So as I'm looking this, I can also just rewrite this as -1 over n plus 1. Is everybody okay? And what this one diverges because it's a p-series. Well, sort of. It's related to the p-series. If compared to 1 over n. Okay, so that x equals 0 converges, or diverges, excuse me. What about this one? This one's alternating, so this converges by alternating series. Now, you guys, ln of x, right? That's the function we're modeling. It absolutely cannot converge at x equals 0. That's why I'm staring at it and I'm saying there's a big problem here. Why can't ln of x converge at n equals 0? Or at x equals 0? It's not defined at x equals 0. Is everybody good? Like when you think about the graph of ln of x. Wait, for you guys it goes this way. So my interval of convergence is 0 to 2.
We always show that we're doing, we would know that it would have to diverge at 0.
You would need to show some sort of justification. So if you were to be like, oh, ln of x is not defined at 0, it can't converge there, I'd be comfortable with that. But like you would need to show the reasoning behind. Otherwise, it just looks like you're making a 50-50 shot. Everybody good? All right. All right, so for this next part, y'all, we're talking through, again, last week I kind of gave you the power series. This week we're finding the power series. So one way to do that is if it's a rational function using the geometric formula. If not, then what we're going to do is use the same reasoning as that Taylor polynomial that we were using at the beginning, like in 9-7, okay? So to find to understand this Taylor series, you're basically doing the Taylor polynomial, and for as many terms as you need to see the pattern. Do you guys get what I'm saying there? Okay, so let's start doing, this is a good opportunity to review that Taylor polynomial. Let's get a couple of derivatives here. And so if my original function is sine, then we have cosine, negative sine, and we all have the same kind of ideas here. After doing the answer keys for the entire unit, going through that sine, cosine, negative sine, etc. Comes really quick. Okay, what's our center? 0. So we're going to say what's happening at x equals 0 for each of these derivatives. So we have 0, 1, 0, negative 1, 0. I'm going to do one more derivative to help us kind of see what's going on. Okay. And are you guys with me that for this particular function, we could do this in perpetuity, right? Like I could just keep going and keep going and keep going. And so to get to an infinite polynomial or an infinite series, like we could do this infinitely. Then we'd get annoyed eventually, I think. All right. So I'm going to do kind of like overall, there's a ... here that keeps going and going and going and going. Okay. All right. So to find my Taylor series, I'm going to start with my polynomial, which I'm going to call P sub n, because we're going to keep going until we figure out a pattern here. Okay, so in this case, it's f of c is 0, because sine of 0 is 0, plus, and then we do the value of the derivative over the term factorial. And again, similarly, I can do ... right? Like, is this, so for a Taylor polynomial, this stops, like, I gave you, like, the number of terms is for a finite number of n. For a Taylor series, we're kind of thinking this is going on forever. That's the biggest difference, okay? And if I simplify this, I get, and I'm going to leave it as 1 over 1 factorial x minus 1 over 3 factorial x to the third, plus 1 over 5 factorial x to the fifth. So if I asked you just in words to describe kind of what are the patterns that you're seeing, what are you seeing?
We're getting all the odd terms with the
Okay, so it's x to an odd power, yes? Okay, what else? Alternating, and my numerators are those odd factorials. Is everybody good? All right, so I can say that sine of x is equal to the sum. My recommendation is you say n equals 0. There's some reasons behind that. To infinity. Because again, it's going to keep, we could keep this going in perpetuity. Okay? So I need to have it alternating. So I've got to decide, am I doing negative 1 to the n, or am I doing negative 1 to the n plus 1? Is everybody good as to why we have to do that? If I'm starting at n equals 0, and my first term is positive, what exponent should I put here? N or n plus 1? Which one will be positive? N. Because then I'm starting at 0. Is everybody okay? All right. My x variable is being raised to the odd power. In order for it to be odd, it's got to go up by 2 over and over and over again, right? So it's going to be 2n plus 1. And I always like to check, okay, at n equals 0, does this term match right now? Everybody good? Right? If I plug in 0 for n here, do I get x to the 1? I'm great. If I plug in 2 for x, or I'm sorry, if I plug in, my next value for n here would be 1, yeah? If I plug in 1 for x, this is negative, or 1 for n, this is negative, and I plug in 2 times 1 plus 1 is 3. We're good. Right? Okay? So I like to check the first couple terms. This becomes 2n plus 1 factorial. Because it's the same, right? It's third, 3 factorial, fifth, 5 factorial. Now, I could very easily, and if you guys did this, I would make sense out of it. We could have wrote this as the sum is n equals 1 to infinity of negative 1 to the n. No, that should be negative 1 to the n plus 1. Now this x would be to the 2n minus 1 and 2n minus 1 factorial. Are we okay? These two things say the same thing because now my first term, this term is n equals 1 instead of n equals 0. And so when I plug in 1 here, this will be even, so positive. 2 times 1 minus, or 2 times 1 minus 1 is x to the 1. Do you guys see what I'm saying here? So I think it's easier whenever possible to start at n equals 0. I think the setting up everything else makes a little bit more sense. Sometimes it's not possible to start at 0. Everybody good? All right, the second half of this question, I ask, where does this converge? So to do that, we're going to do that ratio test. So A sub Guys, what's that limit? 0 less than 1, which means this is always convergent, so it converges from negative infinity to infinity.
If we're making a tailored, like a power series like this, to be infinite, and the goal is to match it to sine of x, right? To approximate it as far out as possible. Why would we ever not have it converge infinitely?
Oh, we didn't make this converge infinitely.
But
The pattern, this particular pattern does converge infinitely. We didn't make this happen.
well,
We didn't.
But,
So your question is like, if I want to look at it, not at this, at a different center, and what you have to do is adjust for that different center in your series.
Yeah. But I guess my point is like, why would we ever have a case where we can't like have a pattern that's going to converge infinitely?
Because not all functions are as well behaved as we would like, right? Like if I tried to do this for tangent, there's no way I could get tangent to converge infinitely because it has discontinuity, right? Like not all functions are well behaved. Cool? Right? If I tried to do an absolute value function this way, start thinking about how absolute values are piecewise, and so then like defining stuff. So the simplified version of that answer is because some things are harder than others. But in reality, now what happens is like in the real world applications of this, so I have a friend who does a very, very different, there's a Taylor series and a Maclaurin series, there's something called the Fourier series that actually turns things into sines and cosines. And for specifically, he's an electrical engineer, so turning stuff into sines and cosines is something he uses, something about electricity and sines and cosines being useful, right? But like, does he do the calculus every time, or does he use a platform that does the calculation for him, but he has to manipulate that platform to get what he needs, right? So having that baseline understanding of what that platform's doing is important. So like, do people typically do this to figure out the Maclaurin or Taylor series? No, they use technology just like we use for everything else, right? Cool? Questions so far? Great, let's. Do a couple more examples. Okay, so I just moved my derivatives because it's the same function. Biggest difference now is we're centered at pi, yes? So now, so sine of pi is 0, cosine of pi is -1. I'm just kind of going to skip over the even powers at this point, right? Because in the zeros, are we all comfortable with that? So some things that like this becomes x minus pi, not just x to the 1, because it's around that center. And so then like when we're looking at different windows of the function, this is how we do it. And then now this will become plus 1/3 factorial x minus pi to the 3rd minus 1/5 factorial x minus pi to the 5th. So now it becomes looking at this, creating that same model. Like I said, I like to start at n equals 0, but I'll be able to figure it out if you start at n equals 1, okay? I think plugging in 0 to make sure my pieces match at the beginning is easier. Okay, so still alternating, right? So now I'm going to have -1 to a power. What power should it be? It should be n plus 1, because now my first term is negative, so I want my power to be odd so that overall value is negative. X minus pi to the, still to the first power, so this will be 2n plus 1. And then 2n plus 1 factorial. Now, y'all, what's going to happen when I do my do my test? We're going to get the exact same thing. Are we all comfortable without going through the whole process that we're going to get the exact same? Instead of having x squared, we ended up with x squared over 2n plus 3, 2n plus 2. Now it'll be x minus pi squared, but it will still be those n's on the bottom. Are we all good with this? Okay, so this also converges from negative infinity to infinity. All right, now, for this next one, we have a little bit of this gets a little hairier, right? Because now, when I go through and I'm starting to think through these, let's see, my derivatives, I have f of x equals the sine of x squared. What would f prime of x be? It would be 2x cosine sine x, right? Wait, cosine of x squared. No, yeah? I think you do. And then I go to do my second derivative. You want me to do it? Just do it? Let's see. It would be, let's see. Fig GIF would be 2 cosine of x squared plus 2x times 2x negative sine of x squared. How are we feeling? Everybody feeling really good about this? Yeah, no, we're not doing this. Are we all comfortable not doing this? This doesn't mean we're not going to get an answer. Is everybody good? So let's, are you guys with me? I'm going to let g of x equal sine of x. And we just figured out, not that long ago, that means g of x would equal the sum of negative 1 to the n, x to the n. Sorry, it was 2n plus 1, right? Like we just did this question not 2 seconds ago, right? Not trying to be, we just did this question. Great. And this f of x is really g of x squared, right? And if I'm finding g of x squared, what I do is I replace all the x's with an x squared, right? Like, so couldn't I just call this done. What do you mean? The same thing as what?
Like convergence,
Yeah, the convergence will be the same. Everybody good? You guys, I did this in your practice packet, which Kira, I'll get you a copy of it. You guys, this cannot be a Maclaurin series because Maclaurin series are centered at 0 and ln of x can't be centered at 0. We'll call it centered at 1. And so when you get to the ln of 1 if you're doing the extra practice problems I gave you guys last week or gave you on Monday, there's one that's a Maclaurin series for ln of x, and we can't do that. Okay, so the intent, center that at 1. So, okay. All right, now, we just said not that long ago that ln of x is equal to this. And we said it like, I don't know, maybe half hour ago. Right? And so what is ln of x cubed? Come in. I'll make them do this. What's up?
Hey, you don't have a rolling whiteboard, do you?
A rolling whiteboard? I do not.
Okay.
Sorry.
Do you happen to know of anybody who does?
I'm sure I did at one point.
That's fine. All right.
After the move and all the stuff going back and forth when we did the renovation, I don't know where any of that stuff ended up. Yeah, I have no idea who would have it. Maybe asking central office might actually, like Jim Buffer might be the one who knows the best because he knows where a lot of that kind of stuff is.
Thank you. Appreciate it.
Sure. Cool? Feeling good? We're